So I never actually built the MOPA version of the 630 meter transmitter. Instead, I went on a little more exotic, more involved project. I wanted to make a two-bander, like a complete station transmitter that could handle 2200 and 630 meters. And I did this back in 2017. It was quite a huge undertaking, and actually it has 10 tubes, 10 valves in this transmitter. It's like a Johnson Ranger without the modulator section, and it was the basis for a two-part article in Electric Radio magazine. Anyway, that thing's been sitting on the shelf, and finally I've gotten it on the air successfully just recently. So I'm going to go through that transmitter, the one I actually built. But do try the MOPA, the simple two-tube transmitter. I think it's going to be a very worthwhile project if you want to just get on the air with a tube-type circuit. Some may ask, why with the MOPA didn't you go crystal control? Well, you could go crystal control. The problem is, how do you find crystals for that frequency? And that's the rub. You really do have to have a VFO-style transmitter when you're building today, because crystals at very low frequencies are fairly rare to find. Here we are looking at the transmitter schematic. It's a little bit scary. We're talking about 10 tubes here, and this is a fairly complicated transmitter, but remember the equivalent transmitter in the 1950s, like the Johnson Ranger, you'd also have a modulator section on top of this. So this is just a pure CW type transmitter. Let's look at some of the key features in this schematic. First of all, I want to look at the way I'm producing the two bands. And the two bands we're talking about are the 137 kilohertz region and the 470 kilohertz region for 2200 meters and 630 meters. The way that I'm doing it is I have a single variable crystal oscillator running at 6.4 megahertz right here. This oscillator runs all the time. It's very stable, and I can wiggle its frequency with these two components here. So we are shifting the crystal's frequency up and down a few kilohertz. Now I take this signal and I put it into a mixer, V1, the 6BE6 mixer, the same one that's in front of, an All-American 5 receiver. And in this case, I'm using a crystal oscillator in this mixer, and I'm mixing these two frequencies with this frequency, and that gives me the two bands. So the whole thing is crystal controlled, but I'm using high frequency crystals to synthesize the two low frequency channels, the one around 137 and the one around 473. Now I take either of those frequencies and just low pass filter them. Okay, so they both sail through and they go into the driver, the 6AQ5. The driver has individual tune circuits for each band, the low frequency band and the medium frequency band. So you select one or the other and you send that into the final, and the final has a wide enough tank circuit that through taps and through various capacitors I can select the high or the low frequency. Some other things that are in this circuit you might be interested in. The keying. This is the keying circuit. It's known as keyed differential timed keying, and this was found in many of the Johnson radios and many other of the radios that had CW as a feature. What this does is it allows the oscillator to be keyed in a very timed way, so that you don't have chirp. Now, I don't have that much chirp anyway because I'm crystal controlled, but in those radios that were VFO controlled, what they would do is they would keep the oscillator just barely biased off, so that it's very, very easy to key the oscillator on and off through its bias right here. And the other part of the circuit is it actually grid block keys through this circuit the finals, and directly influences the driver's grid as well. So it's keying all of the stages sequentially so that you don't get any chirp. Another interesting circuit over here, this is the clamp tube. The clamp tube looks at the bias on the final and the amount of drive. If there's no drive, the clamp tube will cut off the screens of the 6146s, thus protecting them from running away, and it also protects the power supply somewhat. So here's a novel circuit. I've got a SWR, or a power meter here, made of a toroid that comes down to this detector amplifier circuit, and it drives the meter as a power output type of feature. Lots of features with the metering. We can look at that tune signal for the output. We can look at the plate current. We can look at the grid current. And we can look at the medium and high voltages. Here's the medium voltage. The high voltage is here. We have negative bias. Two different types of negative bias. One associated with the final, and one associated with that fancy grid block keying, key differential, sequential keying, or whatever you want to call it. So that's the basic rundown on the transmitter. It's fairly involved, but it is a full-feature CW transmitter. Okay, let's take a look at the back of the transmitter. As you can see, there's a very large radio frequency choke. This is minimum, and it would work very well for 630, but you really need something even larger than that if you want to cover 2200 at full efficiency with a pair of 6146s. In between, you can see there's a neutralizing wire. Neutralization is important with 6146s, pretty much any band, but here on 630 and 2200 meters, those tubes could easily go into VHF or UHF oscillation, and you'd never even know it. So it's best to neutralize them. This large coil is the output for the pi tank. These capacitors isolate the choke from that output tank. So the tank is cold for high voltage. It may look really dangerous. You don't want to put your hands in here, of course. But the only high voltage is where I have this Kapton tape to the tube plates, which have the porcelain insulators, and the actual parasitic chokes. If these should break down, there is a choke in the output down by the SO239 that will short that out and protect you on the antenna terminal. There's always late additions, like this transformer here had to be added for some extra filament power that I wasn't counting on. But basically, here's your FT243 crystals. This is the VXO crystal, and these two are the band switch crystals. Two regulators, one for each oscillator in these two tubes, 6AU6 and the 6BE6. The big tuning capacitor here, and the VXO capacitor variable here. The band switch on top. This is the little meter tube that allows you to do RF ammeter measurements on the output. That uses a toroid. Let's look at the bottom. So this is where you should be saying, oh, now I get it. This looks a lot like your typical 1950s ham transmitter, like an Apache or a Valiant or a little Ranger. You can see all the parts are in there tightly connected between the tube sockets. We have this big multi-section variable that is the loading control on the Pi network, and that's not enough on 2200, by the way. Works okay for 630, but not enough on 2200. Extra capacitors are put in with the band switch to give you appropriate loading. But look at, here's the high voltage over here, built-in power supply. Let me see if I can get on the current meter on the output so you guys can peek in there and see what that's all about. As you can see, it's a toroid. Just goes right to the output, and that feeds that tube, and that gives you RF current measurement. In effect, at 50 ohms, it's a power measurement. So let's take a look at this transmitter. And you know, a nice layout on the front panel is important, and it looks okay. On top, though, a little bit frightening. Everything looks like it was just piled in here, and with no safety cage, I definitely had some regrets. And the bottom, this is an OMG moment, right? It looks like an old Johnson transmitter, the way this is built. And you can tell I was going step by step. You really do need a decent transmitting variable capacitor. You can't use a broadcast type. And even those multi-section jobs that you use for loading up on 80 meters and 160, they're just a toy down here. You really need fixed capacitors to get your loading right. And this big ceramic switch is recommended for the metering. We'll see a little later what happens when you undersize this thing. Any type of decent rotary switch will work good for switching the coil, and I do suggest taps. In a Pi network, you need to handle at least two factors: the input cap and the coil, or the coil and the output cap, or the two capacitors. So let's talk about the choke. The choke looks magnificent, and it worked quite well on 630. Did not work at all on 2200, and I had to add extra inductance to make it work there. The meter, that's a simple thing, right? What's so controversial about a meter? Well, that's where I had the most problems with the whole radio. All kinds of explosions caused by capacitors undersized or just too old, and the rotary switch not being up for the job, zorch, snap. Parts get squeezed together and suddenly there's a boom. They're too close. So watch what you're doing when you're placing the parts inside. I really think that you start to squeeze parts in at the last minute, and that starts to detract from the beauty of the build. And the power sense tube had to go somewhere, so I stuck it right close to the tank. So here's that added inductance that I had to put in to make it work on 2200. It's a ferrite rod with a bunch of turns on it. So yeah, you're in there, you're just adding high voltage capacitors to get the loading right or to get the tuning right, and it ends up looking pretty silly. Finally, how about the safety choke? What's so good? What's so bad about a safety choke, right? Well, it's bad when it starts to affect your output power on 2200 meters. So the safety choke is important. Now in the end, you run out of space completely and you start nailing things to the outside of the chassis. That's always a bad idea. And the tuning resistor that I put right in series before the capacitors and after the rectifiers, that turns out to be a little bit tough. That resistor gets too hot, and we're putting high voltage through that thing. It's not a good idea. To guarantee Class C operation, we need to put about 1.5 milliamps into each 6146. So about 3 milliamps of grid drive to get into good Class C operation, high efficiency. So we go key down, and we have the grid drive here. We have the grid tuning here. So peak the tuning, bring the grid drive up to around 3 milliamps. Good enough. So with about 600 volts on the plate, 550, 600 volts on the plate, the next thing we do is we dip the final to 150 milliamps per tube to get full output. So that would be 300 milliamps, but I don't want to put out that much. Okay, so we dip the final. We can bring it up and re-dip it. See, so that's 200. So that's 100 per tube. So that's probably about 60 watts per tube input power. So that's about 120 watts input power. Now this thing is capable of a lot more power. When we put it in the operate position, and you can get the full output of these tubes. So imagine 2 tubes, full power. We should be able to do over 100 watts output with this transmitter. So one more feature that this transmitter has, beyond, measuring high voltage, medium voltage, grid current, plate current, it's got this last setting in the metering called power. Basically, it's a inline current meter, kind of like this milliamp meter here, this RF milliamp meter. And it kind of is like a tune for max setting. And I'm in the tune position. If I go key down, you can see that it's putting something out. And as you tune, it maximizes. Okay, and that roughly coincides with what's going to happen up here with a power meter. If you look at a power meter, as you tune, right, you can tune for max on that as well. So it is in effect a tune for max setting, and just a handy thing. Loading and dipping the plate is fine, but some people just want to get there quick, and this is a standard power meter setup with a toroid, with the main conductor going right through the toroid, and it's feeding a tube basically for this in a bridge circuit that measures forward power. Now looking down on the transmitter, it certainly reminds you of any of those 1950s type transmitters, like the Johnson Ranger or the Johnson Valiant and so on. However, it is missing one important part, and that is a safety cage around the RF parts. And this thing is meant to be put into a large upright rack and left alone, or put into a single rack case. At these low frequencies, a single rack case should do a good job at shielding the RF. It's not going to do a good job for safety, however, if you're working on it on the bench. However, since we are using a choke and a cap coupling circuit, all of these components are cold. That is, they're hot for RF, but they're cold for DC. So the only place where you can really get a shock with all of this showing is right where I have the Kapton tape on the top of the choke. Everything is somewhat protected. You can still get a hold of the wrong thing. And the other place where there's exposed terminals would be around the metering switch. So those are the places you want to avoid on the top of the chassis. So in the next video, we're going to actually get on the air with you. Before we do that, we have to have an antenna. And I'm finding that my instruments like this Daiwa power meter are lying to me. They work fine on 80 meters, but they don't seem to work down here in 630 meters. So we're going to also discuss what we need to do to measure SWR accurately and power accurately at these low frequencies. Stand by for the next video. How do I transmit a signal on 630 meters?